Okay, so this talk is also about random oracles. So in particular, we're going to look at modeling random oracles and if they're instantiable or not, similarly to the previous talk. So as you know, random oracles model ideal hash functions. So they do this by giving all parties in the system oracle access to a randomly chosen hash function. Random oracles are powerful. They enable security proofs of a wide range of cryptographic primitives with high security guarantees. But however, although the reliance on random oracles is practical, it's also somewhat debatable. And this comes because of an uninstantiability result of Canetti-Goldreich-Halevi from 98, essentially saying that there is a encryption scheme such that encryption scheme with respect to random oracle is secure, but when I instantiate the random oracle with a hash function, it becomes insecure for any hash function. But there's also maybe a slightly deeper problem, and that's related to the fact that there is no formal definition formalizing what it means to behave like a random oracle. Okay. So in this talk, I'm going to talk about UCEs, as you saw from the title. So it doesn't hurt to maybe go through the definition again, maybe with a slightly different perspective. Okay, so let's just start with a very naive definition at modeling random oracles. This is like the trivial definition that you try to write down. So we call a hash function indro, indistinguishable from random oracle, if over a random choice of a hash key, when I give the adversary the hash key and it interacts with a box, which either implements the hash function under the hash key hk or a random oracle, it basically should not be able to decide which one of these two things it's interacting with. So this is the definition of the indro advantage. So clearly this is uninstantiable, and the reason is very trivial. That's because the adversary has the hash key. It just locally computes the hash value of 0 and then compares it to the oracle's answer. And that's it. But however, note here that for this attack to go through, we need to have an adversary which knows a full query. And by full query, I mean the hash key as well as the input to the oracle, which is 0 here. Okay, so let's have a slightly less trivial definition. Let's hide the hash key and see what happens. Well, if we hide the hash key, we get the PRF security. The adversary doesn't get the hash key, it's just trying to distinguish. So we get PRF security. Well, that is somewhat useful, but in the context of hashing, it's not so useful because the hash key is often public in hash functions. So one idea would be to basically split the adversary. So one part gets the hash key and the other gets the oracle. So let's call the two components of the adversary the source and the distinguisher. So here I have split the adversary to source and the distinguisher. The source interacts with the oracle, which is the hash function of the random oracle, makes some queries xi. At the end, it passes some leakage to the distinguisher, which now gets the hash key, and it needs to decide the bit. So the advantage is defined as before. So is this an instantiable definition? Well, for a similar reason, it is not. Because what you can do, you can have a source which basically leaks a query answer pair via the leakage L to the distinguisher, and then the distinguisher just checks if it's coming from the hash function or not. So same reason that's uninstantiable. So a second idea would be to restrict the leakage. We just say that we restrict the leakage in the sense that it should not leak any of sources oracles, queries, any of S's queries. So none of these XIs should leak. And this leads to universal computational extractors, UCEs, that you heard in the previous definition by Bellare, Huang, and Kielvidi. So here's the picture I had from the previous slide. How do we formalize the fact that the leakage does not leak any of these XIs? Well, I run the source as before, but now with respect to random oracle. I can also run it with respect to the hash function, but this is to have a definition which is independent of the hash function. So the hash function doesn't come to this definition. So I run the source with the random oracle, make some queries, and then at the end, the leakage is packed to some predictor, P, which is kind of acting as a subconscious of the source. And the task of the predictor is to come up with an X prime which matches one of these xi's. So the probability that x prime is in this set. Okay? So we call a source S unpredictable if this advantage is negligible for all efficient P. Okay? And we get UCE1 definition. This is the definition from the Crypto 2013 paper, saying that a hash function H is UCE1 secure if the UCE advantage is negligible for any unpredictable S. Okay, so in the terminology of the previous talk, this is computationally, this is the COP notion. Okay, UCE1 security is very useful. It gives, you can use UCE1 secure hash function to instantiate the random oracle in a wide variety of cryptographic primitives, such as deterministic public key encryption, message locked encryption, RK and KDM security, point function obfuscation, OEAP garbling schemes, et cetera, et cetera. So messages that UCs are quite flexible and powerful. But the question comes whether if UCs are instantiable or not. Okay? So here's an idea to see if it goes through. Suppose that we could obfuscate the code of the hash function. Okay? And consider this attack. The source chooses a random value x, queries x to its oracle to get y, and leaks y to d. There should be y here. Okay? Sorry, and leaks to d these two values, the y, and some funny obfuscation of the hash function of the circuit, which when you plug the hash key into it, it evaluates the hash of x on that key. So this is the circuit. So what does the distinguisher do? The distinguisher simply runs this code on the hash key and check if it matches y. So why does this attack? Okay, first of all, once we have such an attack, we need to ensure that it's unpredictable. And for unpredictability, we would need that this obfuscation should hide x. Okay? And it's unclear if there are obfuscation schemes out there which, when applied to a hash function, would actually hide x. So maybe we can change this attack. Maybe we can have a different circuit or a different obfuscation type of obfuscator to kind of make the attack go through. And of course, this comes to indistinguishability obfuscation. So let's just recall what that is. So we call two circuits C0 and C1 functionally equivalent if they basically agree on all inputs. Okay, and the security says that no distinguisher can distinguish obfuscations of C0 from obfuscation of C1. So these two are computationally indistinguishable. And Garg, Gentry, Halevi, Rykova, Sahai, and Waters built indistinguishability obfuscation from lattice-based interactability assumptions. Okay, so let's see how the attack goes. So suppose we have a source which now leaks an indistinguishability obfuscation of this Boolean circuit. So we don't need to obfuscate the circuit and check if it equals y. We just obfuscate the circuit which already has the check hard-coded inside it. Okay? So this is the circuit we're obfuscating, where y is the value that we get from the oracle. D does the same thing as before. It just runs this obfuscated circuit on hash key and returns the result. So if the oracle is the real hash function, then the value that y that we get is the hash of x on their hash key. So this check will pass with probability 1. Okay, because I'm putting the hash key here. If the oracle is random, then this value y is random. So the probability that this check will pass the test would be 2 to the minus size of y. Okay? So the advantage of this source and distinguisher, this adversary, would be 1 minus 2 to the minus size of y, which is overwhelming. But there comes the unpredictability. We need to ensure that this obfuscation that we had actually hides the value x. And recall that we only need to ensure this when the value y is random. And why is this? And this is because on the unpredictability game was defined with respect to a random oracle. So there was RO here. Okay? So let's see how the analysis of unpredictability goes. So by the union bound, for any x value x, the probability that over a random choice of y, there exists a hash key such that this check passes is less than or equal to the size of the key space divided by size of the range. Why is this? This is because for each of these hash values, the probability is 1 over range, because y is random, and then you apply union bound. So what does this mean? This means that if the key space is much less than the range, the size of the key space is much less than the size of the range, then this circuit here is actually identical to the zero circuit. Okay? With overwhelming probability. And now, by the security of Indistinguishability Obfuscator, we know that I/O of this circuit leaks no more information than the I/O of 0 does. Okay? And the latter is independent of x. So the I/O of this circuit would also not leak x. So you might say, what about this condition? Can we drop this condition? Yes, we can. We can consider instead I/O-ing the circuit hash of x1, hash of dot comma x1 equals y1 to hash of xn comma y equals yn for big enough value of n. This, you can basically see this as some sort of a range extension for the hash function. And as a result, we get that under the existence of I/O, UCE1 security is unsubstantial. And this does not contradict any of the instantiations in the random oracle model, including variable input length or fixed input length. Because the random oracle doesn't have a code. We can't annihilate. So can we go around this? It is possible to go around this. Note that I/O is only computationally secure. So how about having a new kind of new definition which allows all the predictors to run in unbounded time? Okay. But this then raises the question whether there is a statistical I/O. If a statistical I/O exists, then I can launch the same attack. But then there's a theorem of Goldwasser and Rothblum from 2007, which says that if a statistical I/O exists, then the polynomial hierarchy collapses. Which is nice, because for those researchers working on impossibility results, this is an example of a negative result, which is used positively to come up with a new security model for hash functions. So here's the definition. A hash function h is statistically UCE1 secure if the UCE advantage is negligible for all sources that are unpredictable, even with respect to unbounded predictors, not just efficient predictors. And with such a definition, well, the question arises whether that definition is useful or not. And it is actually, and one can recover the RK and KDM security model, security of the BRS symmetric encryption scheme. Proofs of the storage protocol, point function obfuscation, correlated input secure, and garbling schemes. And this notion was also independently suggested after our attack by Balare, Huang, and Kielwidi in the updated version of their paper. However, this does not hold for DPKEs, message-locked encryption, OEAP, and hardcore functions. And the reason for that is that the proofs of these rely on leakage, which only computationally hide X. Okay? And we have a notion here which only applies to leakage with a statistically hide X. So BHK introduced two new source classes called parallel and split sources. And they do this by imposing extra structural restrictions on the source. So this split source basically has two non-communicating parts, non-communicating subsources. One part gets X, the other part gets Y. And because they are non-communicating, this would directly rule out the I/O attack, because you would need both X and Y to purport the I/O circuit. And this notion is enough to instantiate random oracles for hardcore application, hardcore function application. For bounded parallel sources, there's a new notion also called bounded parallel sources, and these again have two parts. However, they can communicate to some extent. But the restriction here is that the second part has very low complexity, very kind of small runtime. And these are enough to instantiate DPKEs, MLEs, and OEAP, message-locked encryption, deterministic public key encryption. So using a tool of Applebaum, Ishaya, and Kushelowitz called randomized encodings, we are able to actually show that bounded parallel source security is also uninstantiable. And roughly speaking, this is because we can use these randomized encodings to split the attack into two stages, where the first stage has high complexity and the second stage has very low complexity, which would just finish the attack off. And details of that are in the full version of the paper, which you can check on ePrint. So let me end with some final thoughts. So UCE is a conceptually beautiful idea, and it's real progress after 15 years since CGH98 was published. And it brings added provable security guarantees to practical protocols. And our work brings cryptographic validation to definitions that you can propose within the UCE framework. So we show under I/O that UCE1 and the stronger UCE2, this is the CRS notion, are unstanchable in the standard model. That bounded parallel source is also unstanchable under I/O. But there's good evidence that the statistical notion could be realized, possibly. So the road ahead is actually to look at instantiate or uninstantiate these notions, the statistical, the split. Let me emphasize, we did not break the split notion, and other new emergence notions of UCE security. And also, it would be interesting to look at modeling other properties of random oracles beyond the UCE framework. So as a non-technical kind of comment, I hope that definitions, protocols, and their cryptanalysis keep a friendly relation. And I end there. Thank you.